Hello, people. We're going to get started today with talking about the continuity equation for open systems. Not very difficult in concept. You understand it, and then you all took a deep bath this weekend where you practiced all this. So I'm assuming that we're pros here. So this is just me doing a couple problems this afternoon, that can try to show those concepts, and so I can just spend some more time kind of really getting into depth with them. But basically, the sum of what we talked about is just this equation: the change in the mass of the control volume with respect to time is equal to the summation of all the mass flow rates in minus the summation of the mass flow rates exiting. This is all we have. This is all we need to worry about today. And this is called the mass continuity equation, or the conservation of mass equation, whichever way you want to look at that. And there is one vocabulary word that we need to remember, and we've been dealing with it for a while now, but now it's going to be an everyday steady state. Steady state is the vocabulary word we need to mean, and that's saying the properties do not change with time. And this property that's not changing with time that we're concerned about is going to be the property of mass, not changing with time. And so what that will mean is the change in mass of the control volume with respect to time is going to be equal to 0. So all the problems that we are going to be dealing with, or I should say most of the problems that we're going to be dealing with this chapter are going to be steady state. All the problems on your next exam are going to be steady state, okay? There's not going to be any transient problems here. But I want you to understand there is a time when a system starts up, but it's transient, and then it's going to run along a steady state, and then it will shut down and be transient. We're going to focus in on that main, when it's operation, the bulk of that operation, and that's what we're going to work on. Now, today we have to say, okay, we have to check to see if something is steady state. And if a problem says check to see if it's steady state, we're going to check it. If a problem doesn't say anything about being steady state, and it's a system that we think is running, we're going to make the assumption that it is a steady state system. So we have one today that's going to be not, and one that is going to be steady state we want to work with. And so let's do those two problems. The first one, we're going to have water, and it is entering and exiting a tank. What we want to figure out is the inlet and exit mass flow rates. And we want to ask ourselves the question, is this steady state? Okay, so let's look at this picture of what we're going to draw, this big tank. And the tank, in the inside of it, is going to have steam coming into the top, and it has liquid water in the bottom. And coming in here to the top, you're going to have a velocity 1 that's equal to 20 meters per second. And you have an area 1 that's equal to 10 times 10 to the minus third meters squared. So the area of this pipe, I didn't draw a pipe, but there's a pipe here that's coming in. The area of that pipe is going to be 10 times 10 to the third, negative third. The pressure at 1 is going to be 20 bar, and the temperature at 1 is going to be 600 degrees Celsius. And then there's going to be another pipe down here at the bottom, and there's going to be some stuff coming out, and the velocity 2 is going to be 1 meters per second. The area 2 is going to be 6 times 10 to the minus third meters squared. The pressure 2 is going to be 10 bar, and the temperature 2 is going to be 150 degrees Celsius. And so this obviously is an open system. If I were to maybe draw my system, I'm going to look at this going on here, and I know that there is going to be mass crossing that boundary, and that's the only thing I need to have to denote that it's an open system. And you look at it and you might think, well, that's not steady state right away, because there's 20 meters per second steam coming in, there's 1 meter per second coming out. It's not steady state. But remember, the steady state has nothing to do with the velocity. It has nothing to do with the volumetric flow rate. It only has to do with the mass flow rate. That's the main thing that we have to be worrying about here. So let's just say it said the problem statement said find what the inlet and exit mass flow rate is. And so we go back and we think about what's happening here. We know that mass flow rate is equal to density times area times velocity. Or as we're going to use it, area times velocity over specific volume. Now, area times velocity has a special name, and that's volumetric flow rate. Specific volume is what we've been dealing with all the way so far. We've dealt with specific volume many, many times. And so it looks like for this problem, we're going to need to find the specific volume at state 1 and the specific volume at state 2. We know it's a steam coming in. We know it's a liquid going out, but let's just confirm that. Let's just go through the steps by drawing a TV diagram. We have our vapor dome, and we have two lines of constant pressure, one at 10 bars and one at 20 bars. And we need to figure out where this saturates. And so what we're going to do is we're going to go to our old friend, the appendices, and we are going to go to table A3, because A3 is the saturation table that has nice even pressures. So here we go, table A3, properties of saturated water, pressure table, and we're going to go down here and we're going to look at 10 bars and 20 bars and find out what its corresponding saturation temperatures are. Here's 10 bars is 179.9 and 20 bars is 212.4. Okay, and that's the information that we needed there. So when we go back to our diagram here, we're going to draw at 10 bars, we are going to draw 179.9, and at 20 bars, we're going to draw 212.4, and we know this is all in degrees Celsius. And we're going to look at where we actually are. Well, temperature 1 is at 600 degrees Celsius, it's way up here, and it's going to intersect over there. It's absolutely going to be a vapor. And 150 is down here, and it's intersecting with this line right here, and that's absolutely a liquid. Okay, so just to practice, you could take their word for it, but let's just practice to make sure. And now the question is, what is our specific volume at state 1, and what is our specific volume at state 2? That's what we're going to have to find, those two values. Well, let's do 1 right away. We know it's a vapor. So we're going to go again to our tables, and we're going to go to table A4, which is our superheated water vapor table, and we're going to look for 20 bars. Well, 20 bars is not on the first page, but it is here on the second page. We have an entry for 20 bars, and we're hoping that 600 degrees Celsius is there, and it is 600 degrees Celsius, and so that gives us that 0.1996 is going to be the specific volume. So I'm going to put that on my sheet here, 0.1996 meters cubed per kilogram. Now, for the liquid, we know that water has a liquid table. So we can go to the liquid tables. That's table A5. And we see that there is a entry. The first entry is 25 bar, and we're at 10 bar. So we're well below the first entry. And this table is telling us that the properties of compressed liquid water, they really only start to really change when we get very high pressures up to 25 bars. So we're at 10 bars. Our properties are not on here. So what we have to do is we have to do the liquid approximation. What we would do with anything else is the liquid approximation, and it's a pretty good approximation. We're going to go back to the saturated temperature table, which is table A2, and we're going to approximate the properties for that specific volume to be the same as the saturated liquid at the temperature that we've been given at 150 degrees Celsius. We are going to say that the property of specific volume is going to be 1.0905 times 10 to the negative third. That's going to be what we're going to approximate it as. Okay, the liquid approximation. We're going to use that a lot this semester, so make sure we know that. We have to do it for ammonia, propane, R134A or R22. We will do it for water when the pressure is not very high. So volume 2, specific volume 2 is going to be approximately equal to the specific volume of the saturated liquid at the temperature at 150 degrees Celsius, which is going to give us a value of 1.0905 times 10 to the minus third meters cubed per kilogram. Okay, so now we've looked at both of those specific volumes. And now we have enough information that we can now plug in chug and find out what our mass flow rates are. So the mass flow rate at 1 is going to be the volumetric flow rate at 1 all over the specific volume at 1. I know it's obvious here, but we must, when we're trying to find the state 1, we must find everything at 1. The specific volume at 1, the area at 1, the velocity at 1. At some time in some problems, you may be tempted to use a velocity at a different place to find a mass flow rate at some other place. Don't. You've got to have everything with state 1. It seems very, very straightforward here, but it can get tricky on some problem statements. I've seen it happen. Okay, so our area here is going to be 10 times 10 to the minus third meters squared, and our velocity is going to be 20 meters per second, and our specific volume is going to be 0.1996 meters cubed per kilogram. And we're looking for units of meters cubed per second. And if we look at that, that's what's going to happen. Sorry, we're looking at meters cubed per second. We're looking at kilograms per second. Kilograms per second, sorry. And what I was trying to think of is meters cubed is going to cancel off. So meters cubed just cancel off. And we have kilograms per second that we're going to be dealing with. And so now we know we can do our calculation. We can never do our calculation to a final answer until we're sure that we have the right units. Okay, so 10 times 10 to the negative third times 20 divided by 0.1996 is going to be 1.002 kilograms per second. So about 1 kilogram per second of water is coming in. And for our mass flow rate at 2, again, we're going to take the volumetric flow rate at 2 divided by the specific volume at 2. The area there is 6 times 10 to the minus third meters squared. The velocity is 1 meter per second. And we're going to divide by the specific volume as 1.0905 times 10 to the minus third meters cubed per kilogram. Again, meters cubed goes away, and we're going to have kilograms per second, which is what we need. So now we can do the calculation. 6 times 10 to the minus third divided by 1.0905 times 10 to the minus third is 5.502 kilograms per second. So even though the velocity was smaller, significantly smaller, 20 times smaller, and the area was smaller, we still have more mass coming out at 2 than we do at 1, just because water is more dense, heavier, has more mass to it. So it's easy to say that this is not a steady state process. This is not steady state. We have more mass going out than coming in. That means over time, that level of water in that tank is going to go down. And we need to figure out what rate that is. So our continuity equation says the change in mass of the control volume with respect to time is equal to the summation of my mass flow rate in minus the summation of my mass flow rate exiting. And we only have one thing coming in, and we only have one thing going out. So this is going to be 1.002 minus 5.502, which is going to give us minus 4.5 kilograms per second. So we know that the water is changing. We're losing inside of that control volume, that green thing that I drew up there, we are losing 4.5 kilograms of water each second is leaving that control volume and not being replaced. If it was steady state, everything that was leaving would be replaced immediately. But this is not what's happening here. This is a very straightforward problem with the continuity equation and looking up some properties. We do have that ideal gas, sorry, not ideal gas, the liquid approximation put into here that we have to think about. Any questions about this? Okay. So now the question is, what is the hardest question you can ask in what we're talking about, continuity equation? And that's what the next one is. This is the hardest thing I could think of. Actually, I didn't think of it as a problem that's been picked. So what I'm going to have is I'm going to deal with some duct work here. So here's some fancy duct work. And we have 4 areas we're dealing with. We have here's coming in at 1, coming out at 2, coming out at 3, and coming out here at 4. And right here is an air handler. So those of you who are architecture engineers, handler. Those are architectural engineers you probably dealt with or will be dealing with this in your big building mechanical classes. We have some air coming in, and it's going to go do something in the air handler. Something's going to happen. We're either going to have heating or cooling happening there, and then we're going to throw it out to the rest of the ducts, and it's going to go to the rest of the house, the building. And I'm going to say that the pressure 1 is equal to the pressure 2 is equal to the pressure 3 is equal to the pressure 4. All the same pressure. Not dealing with some wacky situation. We're all in a room like this where we have atmospheric pressure. And I want to give you a lot of properties here. So I'm going to give you the state information, state 1. I'm going to tell you the pressure at 1 is equal to 1 atmosphere. I'm going to tell you the temperature at 1 is equal to 35 degrees Fahrenheit. I do not tell you what the diameter of 1 is, of the duct at 1 is. I'm going to tell you the volumetric flow rate at 1 is equal to 15,000 cubic feet per minute. And I do not know what the velocity is at 1. For state 2, I know again the pressure at 2 is going to be equal to 1 atmosphere. The temperature at 2 is equal to 80 degrees Fahrenheit. The diameter at 2 is equal to 26 inches. I do not know what the volumetric flow rate is at 2, but I know the velocity at 2 is equal to 10 feet per second. State 3 is exactly the same as state 2. I'm going to copy it down just for completeness sake, but it's the same thing. Pressure 3 is equal to 1 atmosphere. Temperature 3 is equal to 80 degrees Fahrenheit. The diameter of 3 is equal to 26 inches. The volumetric flow rate of 3 we do not know. And the velocity at 3 is equal to 10 feet per second. And finally, we have state 4. State 4 has a pressure of 4 is equal to 1 atmosphere. Temperature of 4 is equal to 80 degrees Fahrenheit. Diameter of 4 is equal to 50 inches. We do not know the volumetric flow rate at 4, and we do not know the velocity at 4. That's the information. So from all this, we know that the air handler now is a heater. We're heating up the air. We're taking in very cold air, 35 degree Fahrenheit air, and we're going to warm it up to 80 degree Fahrenheit air, and we're going to distribute it to the rooms that we're dealing with. And I have 3 questions here that I want to answer, and those questions are as follow. A, what is the mass flow rate of 1? What's the mass flow rate of 1? Okay, that's exactly what we did previously. We know that mass flow rate is going to be equal to volumetric flow rate at 1 divided by the specific volume at 1. Now the different thing from this question to what we had previously is here we're dealing with air, and air is an ideal gas. We're going to assume it's an ideal gas. And so we can say that PV is equal to RT. We can't say that about the water. We have to look up the properties for specific volume. But I know the specific volume is going to be RT all over P. So I know that my mass flow rate is going to be the volumetric flow rate at 1 times the pressure at 1 all over the R value for 1 times the temperature of 1. That's what we're going to be dealing with. And we know the volumetric flow rate at 1, the pressure at 1. We can calculate the gas constant at 1, and we know the temperature at 1, so we're good to go. So let's do that. I have 15,000 cubic feet per minute. 15,000 cubic feet per minute. Pressure 1 is 1 atmosphere. R value. Well, I'm going to use, this is English, I'm going to use 1545. That's going to be in R bar. I want to get the bar off of it, so I'm going to divide it by the molecular weight, 28.97. And the units here are going to be pounds, force, feet, divided by pounds mass, degree Rankine. Okay. Again, if I did not divide by the molecular weight, it would be pounds force feet times pound mole degree Rankine. But anytime I want to get away from if I have an R bar, a U bar, an H bar, and I want to get off of those units that are on a molar basis, I divide by the molecular weight to get on a mass basis. And my temperature is going to be 35 plus 460 degree Rankine. I must have my temperatures in degree Rankine every time I'm dealing with the ideal gas law. Now again, before we do any calculation, we need to check our units. We need to check our units to make sure. They asked me for the mass flow rate in in pounds mass per second is what they're going to ask this for. So we had to say, well, first of all, we have minutes here, so I want to convert that to seconds. So in 1 minute, there are 60 seconds. That gets rid of that. Degree Rankine goes away. One of our feet go away. But we have some issues here. We have a lot of extra units here. So let me try to get rid of that atmosphere. I know that in 1 atmosphere, there's 14.7 pounds force per inch squared. Okay, so now that gets rid of my atmosphere. Now it gets rid of a pound force. Inch squared and feet squared. I want to get rid of those, so I'm going to go over here and say that 144 inches squared is 1 foot squared. And that will do it. Inches squared. Feet squared go away. And somebody asked me the other day about this. They don't understand this calculation here. What I'm basically doing is saying 12, I'm doing 12 squared inches squared is 1 squared foot squared. That's what I'm doing. So if you didn't follow what's going on there, because I just went through quickly, that's the conversion I'm having there. So 144 is 12 squared. And now if I look through here, I have units of pound mass in seconds, and I know that that would all work out for me if I multiplied by pound mass on both sides. Now I have pounds mass in seconds. Now I'm comfortable. Now I can do my calculation. I cannot use my calculator until I'm comfortable with my units. Okay? That's the rule. That's the rule I made for myself when I took thermo. Let's make sure that that's okay. Now we type all this stuff in. 15,000 times 14.7 times 144 divided by 60 divided by 1545 divided by 35 plus 460. And then times 28.97 gives me 20.05 pounds per second. That's my mass flow rate at 1. Okay, that's my mass flow rate at 1. Now, even though this problem statement didn't tell me steady state, I'm going to say it's an air conditioning unit. It's running, it's a heating unit. It's running constantly. I'm going to assume steady state here. So if I look at this, the change in mass of my control volume with respect to time is going to be equal to the summation of the mass flow rates in minus the summation of the mass flow rates exiting. I am going to assume this goes to 0 from steady state. And so what I'm going to have is 0 is equal to m dot 1 minus m dot 2 minus m dot 3 minus m dot 4. What comes in with mass at 1 is going to have to leave for continuity 2, 3, and 4. Has to. Okay, has to. So we'll go with that. Now, let's look at the next question that they ask us in this problem. The next question they ask us is, what is the volumetric flow rate at 2 and 3? So B, it says, what is the volumetric flow rate at 2 and 3? And the thing is, 2 and 3 are the same. So we don't have to do two calculations. One calculation will do it for us. And we know that the volumetric flow rate, AV, is going to be equal to the area, which is pi over 4 times the diameter squared times the velocity. And we happen to have been given the velocity in our problems, and we happen to be given the diameter, so we're good to go here. This is going to be pi over 4 times 26 inches squared times my velocity, which is 10 feet per second. Now I have inches squared and feet squared, and I want to have cubic feet per minute. My volumetric flow rate, what I was given to in my problem at state 1, it was my volumetric flow rate was 15,000 cubic feet per minute. So I'm going to put this in cubic feet per minute as well. So I have the same type of units. So again, I know I have 144 inches squared and 1 foot squared. And I know that I have 60 seconds in 1 minute. Let's look at our units here. Inches squareds now go away. Seconds go away, and I have feet per minute that I need to calculate. And so this is going to give me, I have to make sure I don't cross off that 2 there. I'm going to get 26 squared times pi divided by 4 times 10 times 60 divided by 144. And I get that my volumetric flow rate here is going to equal 2,212.2 cubic feet per minute. Okay, and that's going to be the volumetric flow rate at 2 and the volumetric flow rate at 3, because nothing changes there. The diameter is the same and the velocity is the same. If they had a different diameter or a different velocity, we'd have to calculate both. So that is our volumetric flow rate. The last thing it asks me, I'll wait for some of you to catch up because I need to slow down a little bit. The last thing this is asking me is part C is going to be the velocity at 4. I don't know what the velocity is at 4. So for the velocity at 4, I have to figure out how am I going to get to the velocity at 4. I have to find out how to get any information at 4. And if I go back up here and see what I have diameter and I have temperature, but I don't have anything else about 4. Well, I have to remember the fundamental law that's holding this thing together is mass continuity. So I need to find out what the mass flow rate is at 4, and then I can get off what everything else is there. Okay, so I know that mass flow rate at 1 has to equal mass flow rate at 2 plus mass flow rate at 3 plus the mass flow rate at 4. Okay, and I found what the mass flow rate is at 1, and I found what the volumetric flow rate was at 2 and 3. So I can go here and say the mass flow rate at 2 is equal to the mass flow rate at 3 is equal to the volumetric flow rate divided by the specific volume. And again, we can use the same things that we did before. Volumetric flow rate at 2 times the pressure at 2 all over R times T at 2. And so we know here this is equal to 2,212.2 cubic feet per minute times the pressure at 2, which is equal to 1 atmosphere, divided by the R value here, which we said was 1545, divided by 28.97. This is going to be foot pounds force all over pounds mass degree Rankine. And our temperature here is 80 plus 200, not 270, plus 80 plus 460 degrees Rankine. And we'll have to do the same conversions that we did before. So let's go ahead and use them because it's the same equation. 14.7 pounds force per inches squared divided by 1 atmosphere. And then we need to say that there's 144 inches squared in 1 foot squared. And then we also need to say that in 1 minute, there is 60 seconds. And even though I did them again, I want to make sure these things cancel out. Atmospheres goes away, inches goes away, minutes goes away, pound force goes away, cubic feet go away, degree Rankine goes away, and we have pounds mass seconds. And if we do the flipping around things, that's going to show us that that's the right units, and we're good to go. And so now we have to see if we can plug it into our calculator properly. 212.2 times 14.7 times 144 divided by 60 divided by 1545 divided by 80 plus 460 times 28.97. It gives me that my mass flow rate at 2 is equal to my mass flow rate at 3, which is equal to 2.71 pounds mass per second. And now I have these two things, and I'm only left with my mass flow rate at 4. Okay, so I can find that my mass flow rate at 4 is equal to my mass flow rate at 1 minus 2 times my mass flow rate at 2, which is equal to 20.05 pounds per second minus 2 times 2.71 pounds mass per second. And that is 14.63 pounds mass per second. That's going to be my mass flow rate at 4. And I could check that just to be sure. 14.63 plus 2.71 plus 2.71 has got to equal 20.5. Has to. That's the whole purpose of this mass continuity. Has to, has to, has to, and it will. And it will. Okay? However, we're not trying to find out what the mass flow rate is. We're trying to figure out what the velocity is. So remember that the mass flow rate at 4 is equal to the area at 4 times the velocity at 4 all over the specific volume at 4. So that's going to lead us to that the velocity at 4 is going to be equal to the mass flow rate at 4 times the specific volume at 4 divided by the area at 4. And we're going to use that the specific volume at 4 is going to be equal to RT all over P. And so we can plug that in, and we're going to get that the velocity at 4 is going to be equal to the mass flow rate at 4 times the R times the T divided by the area at 4 times the pressure at 4. And now we got more units to work with. Plugging it in, checking to make sure we got everything correct. Okay, mass flow rate at 4 was 14.63 pounds mass per second. R value, 1545 divided by 28.97 pounds force feet over pounds mass degree Rankine. Our temperature here is 80 plus 200 plus 460. I'm getting desperately close to trying to make a mistake here in front of you and put my conversions wrong for Kelvin and Rankine. My area is going to be pi over 4. This area is 50 inches squared, so 50 inches squared. My pressure is going to be 1 atmosphere. Okay. What's 1 atmosphere? Well, 1 atmosphere is going to be 14.7 pounds force per inch squared. All right, let's check our units before we calculate here. Pounds mass is going to go away. Degree Rankine is going to go away. Pounds force is going to go away. Inches squared is going to go away. And atmospheres are going to go away. And we end up with feet per second, which is what we need. Always feels good when our units work out. We think, okay, even if I type it in my calculator, right, I have a pretty good calculation. That's a good, if you check your units on every problem and make sure your units work out, you can get yourself in a really good place. A really, really good place. Okay? Calculator errors on the exam are worth like 1 point. So like to see units working out. 14.63 times 1545 times 80 plus 460 divided by 28.97 divided by 14.7 divided by 50 squared divided by pi divided by 4. I get that the velocity of 4 is 14.597 feet per second. So 14.6 is what I should go with for my velocity of 4. Okay, and that is my answer. Now there is one last thing that I want to talk about on this problem, and that is we have said that mass flow rate 1 is equal to mass flow rate 2 plus mass flow rate 3 plus mass flow rate at 4. That is true. That has to occur. But what students all the time want to do is the following. They want to say that the volumetric flow rate at 1 is equal to the volumetric flow rate at 2 plus the volumetric flow rate at 3 plus the volumetric flow rate at 4. Say, hey, 15,000 cubic feet per second come in. If it's starting a steady state, 15,000 cubic feet per second have to come out. But that is actually not true. That's not true. And let's just look at the numbers. I did some of these numbers to calculate it for us. We had 15,000 coming in. The volumetric flow rate at 2 and 3 were 2212.2 plus 2212.2. And if you use this velocity at 4 and took it times the area at 4, you would have got 11,936.4. So you end up with 15,000 is equal to 16,360.8. And that is not equal to each other. And the question people often ask, well, why? I don't understand, Dr. Winkler. If it's steady state, it doesn't make any sense that you can have more air coming in, going out than coming in. And my question is, what do you mean by more air? The mass of the air that comes in and goes out is the same, is absolutely the same. The volume of that air has changed, and it makes sense that it should change. You're coming in colder air, it's tighter packed together. You heat it up, it's going to expand a little bit. It's going to be a bigger volume. Same air, just just filling up a bigger volume. That's all it's doing there. So if I were to give this to you on the test and I were to say, I have a situation that's 15,000 cubic feet per minute coming in, and it's going out at 16,000 cubic feet per minute, is that problem guaranteed to be steady state or not steady state? And you would have to say to me, I don't know, Dr. Wanklin. It could be that it's not steady state. Could be, because volumetric flow rate is not what I look to check on things. I look at mass flow rate. I have to know my mass. If you give me my mass flow rates, I can figure it out. If you give me some more information, I can figure it out. But I can't tell you by volumetric flow rates. I could give you a volumetric flow rate of 15,000 cubic feet per second and 15,000 cubic feet per second. They could match up, and it can still be not steady state. Because it could be a very hot situation, air coming in, and then it can condense to cold, and that wouldn't work. Just a lot of things we know. Just remember, it's got to be mass. It has to be mass. Okay? I think that's proper English. It's got to be. All right? What questions do you have about this? That's what we have. Today in the lecture, we go over the energy equation, and we will be talking about the energy equation for the rest of the time before exam 2. So we're going to be doing problems of the energy equation on Wednesday and Thursday, or Wednesday, not on Thursday, Wednesday and Friday and Monday and Wednesday and Friday. We're going to do those energy equations a lot, okay? So really today's lecture, video lecture, is the last new material for the next exam. We're just keep practicing it and practicing it, practicing because we can apply it in many different situations. So you should feel very comfortable with the first law for open systems by the middle of next week. It's just to make sure we keep ourselves connected to those closed systems. We're still going to be dealing with ideal gases, still be dealing with those constant and variable specific heats, everything we did before, but a lot of practice on those open systems. Okay, that's what I have for you. Have a good rest of your day, and we will see you